very rich background both in machine learning and logic programming. He's currently at Google Research and also a joint position at Carnegie Mellon University. He has several achievements both in machine learning and especially in integration between logic programming and deep learning, serious heavy deep learning, scaling up to very large databases. So let's then project the talk and welcome him. So ready for the live stream from help desk if available.
You can start. Okay. Professor William, can you unmute you? Okay, perfect. Thank you.
Can you hear me now?
Perfectly.
Great. Can you see my presentation?
Also.
Great. Well, let me go ahead and start then. Thanks so much for having me. I'd like to start out by saying this is actually joint work with many other people, including Pat and Livio, who were at Google with me, and Haichin Sun, who did a lot of this work while he was at Google, and is now back finishing his PhD at CMU. So before I kind of give you a heads up on what I'm going to talk about, I wanted to start with a little bit of nostalgia. So I believe this slide is from a talk I gave in the inductive logic programming workshop in 1993. Could have been 1995, but I think this was 1993. So this is a community I've been following and for quite a long time. And I decided to kind of organize my outline sort of as a tree, right? So this is just sort of like, you know, a hierarchy of different kinds of logics that people have studied over time. And the focus of the first half of my talk will be neural knowledge representations. And, you know, this is really very much a continuation of the kind of work I was doing back in 1993. So back then I was looking at specifically subsets of data log, you know, and I was looking at these very highly restricted, syntactically restricted versions of data log and trying to answer questions as to whether they were learnable or not in various formal models of learnability, which, you know, at the time seemed like a useful and productive thing to do. So I was trying to draw these lines between kind of good languages and bad languages. And what I'm doing here is also looking at many different languages and sort of trying to draw lines between them. And the big line I'm drawing here is between languages that where the operations of the language can be encoded by numerical differentiable operators, and ones that can't. So this is really about developing and using neural knowledge representations as opposed to just any knowledge representation. And also how you can use these things for certain NLP tasks. So the task I'm going to be focusing on is question answering, where there's a natural language question, and that natural language question is answered in one of two ways, either by using text as a resource, as a repository of information, just a large corpus of documents, or by using knowledge base. So this is what I'll be talking about during the talk, you know, essentially the way I'm going to propose doing that, or the way I've been exploring, is to take these neural language models, which are widely used in NLP nowadays, and talk about how to integrate prior knowledge, declarative knowledge, in some sort of neural knowledge representation with these language models. So I think we have plenty of time for the talk. There's an hour and a half scheduled, is that right, Paul? Is that right?
The official time is an hour.
Okay, great. So I will keep myself moving along then. All right, so let's first talk about putting logic into a neural network. So 3 years ago, I came here and I talked about a project which was already a couple of years old at that time called Tensor Log. In Tensor Log, the idea was to look at a neural implementation of probabilistic deductive databases. So deductive databases, of course, you know, the probabilistic version that we were considering are essentially where you add some sort of confidence measure to each ground fact in the database. So this sounds like a bit of a restriction, but in fact, it's not too much in one. There's syntactic tricks. If you want to add a weight to a rule, you can do this by just adding, you know, one kind of specific, you know, fact that only fires in that one rule and give a weight to that fact. So this is actually a fairly broad class of soft logic programs. And there's a natural way of trying to neuralize this sort of thing, which has been used many times in the past. So you've got your database facts, and you've got a set of all possible inferences. So these are all the things in the airborne base. You'd like to figure out whether those should be considered true or false according to your theory. So you basically, you know, have some little neural module that takes, you know, a binary signal connected with each of these facts, combines the ones that are inputs to a possible rule, the ground version of the rule, and then assigns as an output the binary indicator or soft version of a binary indicator for one of these other potential inferences. So this is the basic idea. It's called grounding the logic program. This has been going around, this idea is at least 30 years old. The same sort of like grounding strategies are used by many other sorts of soft logics. There's a lovely survey on this that Lisa Couture wrote a few years back. And you can kind of think of this, if you're inclined to think about things in terms of probabilistic graphical models, as a model where you've got one binary random variable for each fact in the airborne base. And this is a very clean and pretty way of formalizing the problem. And in my view, the only real problem with it is that although it's elegant, it doesn't scale very well. So having one one random variable or one neuron for every possible fact that you want to infer is too many. A few years back, I started looking at an alternative version of an alternative way of formalizing logics, which are based on message passing, where the messages are actually soft sets. So just to give you a brief idea as to how this works, let's imagine I've got, you know, this one clause logic program, and I've got a query, who is the uncle of Liam? Okay, so we can start out by associating X with a set, which just contains Liam with probability 1, okay? And then I can ask, well, what would happen if I use the constraint imposed by the parent relation? Sorry, it's a little bad. I think I've got child instead of parent, but the constraints by the parent relation to see what are the possible parents of X, and you can come up with another soft set, okay? And then that would sort of continue until you got to an answer for the values for Y. So what's essentially happening here is you have a factor graph. And the factor graph has one random variable for each logical variable that appears in your proof, okay? And each of those random variables doesn't encode a binary indicator, okay? Instead, what it encodes is a multinomial. So it's a distribution over database constants. So it's a set, a soft set of things. And you got one factor for every literal in your logic program. So we've got a factor for parent and one for brother. And belief propagation is actually quite efficient on this. It scales linearly with the number of database constants and the number of logical variables you need to do the reasoning in your program. And you know, if you know the program is sufficiently complex, you know, it may scale in the number of loops or recursive iterations you have to do. So so this is a much more efficient approach. There's some pros and cons. One disadvantage is it only works for certain types of programs. So in particular, only works for binary predicates. And it turns out to be a special case of something which is much older. So it's a special case of stochastic logic programs, but it's a nice special case because the process of propagating these sets and altering these sets is actually a linear operation, not in terms of time complexity, but linear in terms of matrix algebra. Okay, so the output message for parent, if you're encoding these sets as one hot vectors, where you've got like a long vector with one component for every database constant, the output message is just a matrix multiplication. So this is something that's very easy to implement efficiently using neural network machinery. So this is very well suited to implementation on various deep learning platforms. And just to give you an idea here, here's some numbers for inference. And this is comparing the inference algorithm, the speed of inference with, let's look now at this red line, which is the version of the code that runs just on an ordinary accelerator with just ordinary matrix operations. So it's running on sort of SciPy and Python. And I'm comparing it to this blue line, which is a more traditional logic programming system. It uses a lot of kind of fancy techniques, including a Warren abstract machine and so on. So this is as fast or nearly as fast. So here we're looking at queries per second, so you want to have like a high number. Okay, and it's often faster when you can use an accelerator, which is that orange line. But the beautiful thing about this, again, is it's also very easy to derive a learning algorithm. So to derive a learning algorithm, you just run the inference algorithm and compare it to the target values, and then you sort of backprop to whatever your parameters are. So here the parameters would be the weights or these rules or facts. So it's trivial to implement that algorithm, and you can exploit all the work that's been done on optimization in neural networks. And you can also exploit the fact that modern accelerators are architected to do exactly what you want to do in learning. So they're architected to do the same operations over and over again. So even though the inference isn't all that much faster, the learning is much, much faster. So we can get sort of like a 500x speed up on a small deep learning problem. And this is like basically deep recursive inference, inferences that are kind of challenging in many settings. So these are inferences that would take quite a while on something like, say, Problem 2. And you can also do learning in cases where you couldn't really do it at all. So this is kind of where I was a few years back when we met in lovely Ferrara, Italy. And one of the properties of this system is that you have this message passing process, which you can turn into a neural network and optimize with neural techniques. And that process is actually something that's declaratively defined by a message passing process, which is a good thing, or maybe it's not a good thing. So in Paul's lovely talk just before this, he discussed some of the issues involved in getting data scientists that aren't necessarily trained in logic programming to make use of the power of those techniques. And I had a number of the same experiences when I went to Google. So I thought to myself, well, what if you just specify this message passing process directly? So that keeps the programmer a little bit closer to what is happening, which is a good thing. And maybe it wouldn't be quite so ugly. So people aren't quite familiar with database query languages, and these models are specified with functional programming. So maybe there's a way you can have sort of a functional version of this that still looks reasonably elegant. So so after looking at Tensor Log, we can now sort of like check that one off on my big outline. I started looking at a version of that which had the same expressive power, but was defined as a query language. So the query language looked a little bit like this, and I think I was just starting to work on this back when I talked at this conference in 2018. So looking at some Python, you start off and you create a context object, which lets you do things like declare the schema and load data and so on and so forth. That sort of stores your data. And then instead of rules, you basically have operations you can do. So one operation you do is construct a set. So this is a singleton set of type person that is just Henry VIII of the House of Tudor, so that's the name of that entity. And then if I want to take that singleton set and do the equivalent of passing it through a wife predicate, I can do that with this syntax, and that gives me another weighted set. So as you may remember, Henry VIII had 6 wives, so that would be the output of that set. And you can do other more complicated things. So this formula is the grandsons of Henry VIII. So all these expressions always evaluate a weighted set of entities, and every expression is basically describing a message passing operation. There's also a second order construct. So you can also have, instead of a specific predicate that corresponds to a specific matrix in your underlying representation, you can specify a variable. So this is a weighted set of relations. So this lets you follow some relation path which is specified. Let's say if you wanted to get exactly the same result as this one, in the first case you could say the first relation is son or daughter, and the last one has to be son. So that would give you again grandson. But you can also have these relations which are simply weighted sets of a special type of entity, can also be soft, and that makes it possible. They're essentially simply vectors over the set of relation constants. So they're just a weighting, and those are things that can be produced by another neural network. So this was the language, and one property of the language was essentially that every operation that was needed in the message passing algorithm for Tensor Log was represented directly in this language. So it was clearly something that generalized the expressive power of that language. Everything, all the sets are stored as these long k-hot vectors. The relations are stored as adjacency matrices, which were, of course, sparse matrices. And this is actually a very efficient implementation. So the knowledge base just needs 12 bytes of memory for every knowledge base triple. And you can distribute this over multiple GPUs, so you can handle inferences that involve moderately large databases, say tens of millions of triples, tens of thousands of relations. Okay, so this is the idea. So what can you do with this? So the main application I was looking at was question answering over a knowledge base. So just to give you an idea how this is normally done, you have some question, okay, in natural language, and that gets compiled into a structured query. And nowadays, this is usually done with some sort of sequence-to-sequence neural network. So come up with a semantic parse of the question. So you train it on inputs and outputs, and hopefully it will get the right result. And then you pass things over to a symbolic query language to give you the actual answers. So the advantage here is that we can make the entire process neural. So then instead of having to collect answers which are a question and its structured, query language parse, you can simply get the question and the desired answers. And when you run a process where you construct a predicted parse, you predict the answers, you look at the loss, and then you basically can back propagate all the information, that loss, all the way through the system. So specifically to use NQL, what you'd do is you'd have some neural network, F1, F2, and so on, which produce the parameters you need for a template. Okay, so you'd have some template for the kinds of questions you care about, or some set of templates. So there's no structure learning here. And you just minimize loss by backpropping through the neural network. So this is what the intended application of NQL was. And the main use of the knowledge base here and the query language is just simply to translate losses in terms of target answers to losses in terms of these natural language processing components that derive the relations in this case. So this actually works. So So this is a well-studied problem. It's an old problem, relatively simple, but there's 40 million triples, 12 million entities, about 700 relations. This is the set of templates that I used, and these neural questions are neural networks that are used to derive these sets of relations are very simple ones. So there was nothing kind of fancy here. And here's how it works. So this is NQL. This red line is a sort of plausible neural baseline. These other colors are other state-of-the-art models. So you can see for all of these problems, which are, I would say, simpler, more regular versions of the Web Questions SP data set with a smaller knowledge base and more regular questions and fewer relations, we're getting basically state-of-the-art results. And for Web Questions SP, well, let's come back to that in a little bit. So NQL was, I thought, a pretty cool idea. But after looking at it more carefully, I decided it wasn't really enough to solve this problem. So to explain why I think it's not enough, I'm going to take a little bit of a detour here and talk about some other problems that are well studied in the neural network world. So one of them is knowledge-based completion. So I imagine many of you have read something about knowledge-based completion. If you haven't, it's not a big idea. It's not a complicated idea. The idea is we've got some true triples, so these are things we know are true, and we'd like to generalize from those to plausible ones. So, given the fact that William Cohen works at Google and he's a co-author with Hai-Chin Sun, maybe Hai-Chin Sun works at Google. That's a plausible generalization. And the way this is done is there's always some sort of neural function where you have a vector encoding for each constant and each relation, and it gives you some number. That's your confidence that that's going to be true. So it's basically doing a similar sort of take on the old problem of predicting members of the airborne base. So this is a little bit like, but also a little bit different to logical inference. Okay, so in logical inference, we've got true triples and true rules, and we derive things that are logically entailed. So that's another way of going from one set of facts to another set of facts. We're looking at ones that are just logically derived. And that's a very well-defined process. And you can sort of imagine, well, what happens if you try and do both? Well, that's a really good question. And until recently, there wasn't a whole lot of work on people trying to do both. So most of the work on generalization basically looked going from true triples to plausible triples and didn't have anything to do with query languages or logical inference. Okay, so there were a couple of systems that basically tried to do this, in the context of a query language. So you're trying to find plausible answers to a query, which is very close to this, but all the evaluations were done on facts which weren't logically entailed, but were plausibly entailed, if you like. And in NQL, I was really focusing on this part of this picture, on getting things that were the correct answers to a query by using differentiable methods. So that's a difference. And is that a good difference or a bad difference? Well, arguably in this case, it's a good difference. So you've got your natural language query, you've got this sort of latent template structure, and you've got your loss. So if you had something that kind of generalized a little bit, okay, what would that do? Well, it would somehow generalize the predicted answers. And probably, it kind of depends on the data set, but probably that would just surface as noise. So that would make the learning harder. Okay. But there's also a downside. Okay. So the way I constructed NQL, all the logical inference was correct. But it also turned out to be very hard to predict these relation sets. So these relation sets, it's simply a neural function that predicts a vector. So that doesn't sound like a hard thing to do. And let's look for a little bit at popular techniques for doing this. So this is, again, another little aside. So maybe some of you guys have studied transformer language models. I'll tell you a little bit about them if you haven't. So these are deep transformer networks. And what they do is they input some set of words, and there's typically some set of words are removed. So there's a mask right? Or maybe these are just things that are sort of later on the input stream that you need to predict. But there's some set of words that you need to predict. Okay, so these are really big networks. They tend to be large. And how do you do one of these predictions? Well, you're going to predict everything on the output side. And the way you predict it is for every possible word in your vocabulary. So maybe there's like 20,000 or 50,000 words in vocabulary. You have a vector. That's a learned representation of that token in the vocabulary. All right. And when you want to predict a vector here, what you do is you don't do a 20,000 way classification process directly. Instead, what you do is you construct a query vector, okay, and you use that query vector and compute dot product differences to each of the things in the embedding. So these are your embeddings. I've gone down from 20,000 to 4, okay, and you construct a query and you say, okay, now what I'm going to do is I'm going to use distance between that query and these examples. So this query is much closer to 3 than the others, and maybe it's a little bit closer to 4 than these other two. So that would turn into a probability distribution, and that's how you do the prediction, okay. So this is great because instead of having, you know, a space of 50,000 or 20,000 tokens, you have a space which is maybe 100 real numbers. Everything gets encoded into 100 real numbers as an embedding table. So it's a much lower dimensional problem, and it works. You can learn pretty accurately. Okay, so that's the way most logic. That's the way most neural systems predict into a high dimensional space. And MQL, I'm trying to predict into a high dimensional space, but I'm not using that technology. Instead, you're basically making something which is 700 independent predictions. And there are ways we can sort of patch that up, but that hurts you a lot. So if I look at the state of the art for this problem, MQL is actually quite a bit behind it. Okay, so how do we fix that? So this takes us to the next part of my knowledge representation tree, which is distributed versions of these set-based query languages. So this is work that was done a year or two back. I came out in NeurIPS last winter. So the question is, how do you use these differentiable operations on embeddings and still get accurate inference? Because I still think it was important to be faithful to the underlying logic. So this is what we came up with. So every set is going to be encoded by a pair of things. So one of them is the centroid of the elements in embedding space. So this is a geometric thing in continuous space. So I'm going to assume all my sets are small and that they are sort of like compactly represented in embedding space. So I can't do everything this way, but I'm going to look at this sort of particular type of set. Okay. So the second part of the representation is a sketch of the set. And particularly it's a Countman sketch, which assigns a weight to every element. So if you're not familiar with these, again, it's like you don't have to know a lot. It's a randomized data structure. Everything you need to do with it is differentiable. Okay. You don't need a sparse matrix to represent it, which is nice. So sparse matrices are implemented in many deep learning setups, but they're not as well integrated with modern accelerators and the fast accelerators as dense matrix operations. And the sketch can actually be pretty small. When small, I mean maybe like a few thousand entries for the case that I need, about 4K. As long as you don't query it too often. Then if you query it too often, then the randomized data structure proofs start to break down. You'll get lots of false positives. So you need a way to check the sketch, but not check it too often. So that's where you use the centroid. So to figure out which things are in the set representation, you basically find some small number of things that are close to the centroid. And it turns out there's a way of doing this very efficiently in neural settings. So if you know that the set has size m, so maybe the set is size 100, then you'll take the top 1,000 things. Okay, it'll be 1,000. And then you rescore those 1,000 things using the Cat1 sketch. And since you only query it sort of a few times, you don't really need a very large sketch. So this can be efficient and it can be very accurate, as long as the set is compact in embedding space and isn't too large. So if you think about the centroid, what it's basically doing is it's giving you a fine-grained type for the elements of X. So you can assume you can represent those types, but not necessarily the details of the relations. And the nice thing about this is now if you want to predict, you can kind of focus on this geometric part of the thing. So to predict something, you just predict a point in embedding space like we did before, and then let the sketch be vacuous, something which sort of just gives a 1 score to everything. So now you're predicting an embedded representation instead of a whole bunch of entity IDs. So predicting things in this formalism is a lot easier. So Countman sketches are also closed under intersection and union, so it's very easy to do those operations in the setting. The last one we'd have to worry about is this follow operation, which is basically, taking a set of objects, a weighted set of objects, and then kind of pushing it through a weighted relation, a weighted set of relations. And this is also actually pretty easy to do. So what we're going to do is we're going to explicitly build a knowledge base by basically concatenating together the relation subject entity, object entity representations. Again, I'm just assuming everything's binary. And then to query this, I basically construct a query which has a representation for the relation and the subject entity as a set. Okay, in other words, as a centroid. So I'm finding all the things that are close to that centroid. I find the top k things of those. Again, that should be fast. It's relatively accurate, but if you want to check and make sure it is really accurate, then you can use the centroids for x and for the relation. So that will be extremely accurate. And then at the last stage, you have to do an approximation again, because you have to take that set of things and convert it to the centroid sketch format. So as long as the inferences you want to have, as long as the operation you want to do, like who are the former students of William Cohen, that's my query. As long as that ends up in a sort of like a compact geometric area and embedding space, and as long as that set's not huge, then you should be able to convert it into this format. And this is efficient, okay? And empirically, it's faithful for a lot of settings. And this is quite different from prior approaches. So in prior approaches, a relation was basically described somehow geometrically in the embedding space. So if you wanted to go from the subjects, professors, to the objects, former students, there had to be a geometric relationship between the real numbers that encode those things. And that turns out to be very hard to do because there's really a lot of kind of random noise. William Cohen works for Carnegie Mellon University, but why couldn't it have been Max Planck, right? William Cohen works for Google, why not Facebook, right? Maybe there's just some chance involved in these things, and that makes it hard to represent. Whereas actually explicitly representing the associations in a big table has a lot more capacity. It has a lot more ability to faithfully modify things. And then the only generalization you have to do at the end is once I've figured out what actually corresponds with x4 and x3, then I need to generalize those, okay, by constructing this centroid sketch representation. And of course, there's a possibility for doing additional generalization if I want, because I can sort of at any point decide to ignore the sketch part of it, which is sort of the fine-grained detail. So this isn't quite like NQL. So in particular, it has to be pre-trained. So to train it, you basically have to give it a whole bunch of inferences that you expect it to do. And we had a process for generating some small set of inferences. So we basically just did examples of these follow inferences and the union inferences, and then trusted the system to sort of compose those things to make more complex queries correctly. And once you've trained that, then you fix all those embeddings and you just train the rest of the model, just as you did with NQL. All right, so we've got our inference algorithm, we believe in that, and we just train the other parameters. So here's some examples. This is one I haven't shown you before, but this is a bunch of synthetic examples that were put together by these guys that wrote this query to box algorithm, which I mentioned before as being one of the few systems that looked at generalization of answers for queries. So there's a sense in which these queries, the answers to these queries could be logically entailed. That's not, again, that's not what they were looking at. They were looking at sort of plausible entailments. Here I'm looking at things that are actually entailed, and I'm trying to measure that performance. So if you look at query to box, it actually performs pretty poorly. and MQL is pretty accurate. So it's up in the 90s. Query to box is usually below 50%. This is a fairly forgiving measure. And if you discard the sketch, you see just the extra capacity you get from doing this lookup in a table of embeddings actually also gives you a good fraction of that gain. So MQL minus is basically not using this fancy sketch idea, which I think was pretty, but maybe it's not always necessary. And then if we look at using this for the WebSQ SP problem, where if you recall, MQL was way below the kind of standard state of the art. So MQL actually does much better. It's close to the state of the art. And the only reason that it wasn't state of the art is actually I was using a very simple set of templates. And I was using those because I didn't think MQL was going to work that well anyway. So if you add one more template to kind of handle the kind of rare cases, then you actually do, we actually were able to beat the state of the art at the time. So this now brings us kind of to the end of this kind of discussion of my work on differentiable languages that are designed for representing knowledge. So these are essentially differentiable methods for doing set-based queries or data flow operations on sets using distributed representations. So I've shown some cases where that's useful, and now I'm going to talk about what I really want to do with it, okay, which is embedding this into neural language models. So I'm sure many of you guys have heard about some neural language models. So you know, things like BERT and T5, and more recently GPT-2 and GPT-3 have gotten a lot of press, and legitimately so. I mean, there's a reason why, you know, even, you know, non-AI experts, people like Elon Musk, you know about these things. And that's because they are now sort of the dominant way of doing natural language processing. So there are were a whole bunch of approaches to natural language processing, very complex systems that people wrote, and that was, you know, an active research area until maybe, you know, 3 or 4 years ago. And now almost all the modern research is basically based on using these large language models that you can then fine-tune for particular tasks. So what I'm going to talk about is taking these models, which were initially designed just for modeling text, so that's why they're language models, and extending them with prior knowledge in the forms of a knowledge base and the ability to reason with that knowledge. And reasoning basically mean MQL without the sketches. So that's the thing I've been using in most of these cases. So let's talk a little bit now about this corner of the picture, this part of natural language processing. So how do you take a large language model, like a transformer language model that I showed you a couple of slides back, and augment it with knowledge? And why do you want to do that? Okay, so like I said, most recent NLP, you take a whole bunch of raw text, you build this neural language model, which basically sort of tries to predict patterns in that text. And then you fix that. And then you take it to like a whole bunch of different applications. So you've got some specific task data, and you run that specific task data through that language model, which is called fine-tuning, and get your results. And this is kind of drawn to scale. So there's a lot of raw text. The models are very large. Billions of parameters is kind of common now. And one thing that's quite interesting is because these models have basically been trained on, you know, many, many documents, they seem to know a lot. Okay, so a couple of years back, there was a paper called Language Models as Knowledge Bases. And they sort of asked this question. So knowledge, the language models they were looking at were trained to fill in missing words. So if you have this mask that it's going to fill in that mask word with some plausible answer. So maybe it will fill that one in as Florence. So you can take a knowledge-based triple and turn it into a little template that asks the model to fill in an answer. And you can sort of see how accurate it is. So these are some of the sort of things they looked at. So the first question here is Francesco Bartolomeo Conti was born in blank. And I don't know if you know the answer to that question. I don't know the answer to this question. If we weren't on Zoom, I'd ask people to just shout out an answer just to kind of break the monotony of listening. I'm not going to sort of break things up and ask people to post things in the chat. But anyway, the correct answer is Florence. And the answer that this language model likes best is Rome. Second, Florence. Then Naples and Milan. So at least it knows this guy is Italian. That's good. I don't know if it really knows that person's name, but it knows something. And here are a bunch of other things that it knows. And it seems to be often very plausible. Okay. And the cases where it's not the expected answer, the answers don't seem to be terrible. Gordon Scholes is a middle member of, do you spell labor with a U or no U? I would have gone with a no U, but I'm an American, so who knows? Given that these models already know a lot, why am I trying to do this? Why am I trying to integrate knowledge and reasoning into it? So I'm not sure that's a question that really needs to be answered for this audience, but one reason is maybe it would be better if the language model was just trained on enough text to understand language, right? As opposed to all the background facts of the world, right? So background facts of the world, people do change political parties, I hear, in rare cases. People certainly go from one job to another, companies get acquired and change. You'd also like to be able to kind of build in compositional reasoning. And finally, you'd like just to kind of I would say, eliminate some of the mystery behind these models. So it's wonderful that you can take a model out of the box that's just trained to do this simple task and ask it questions about the world and get answers. But it would be nicer if you were to use those answers for something important, if you understood why it was doing what it did. So that's the motivation here. And let me start by talking about a project which was not my work, work of colleagues at AT&T. And this is really the first step that anybody would want to do to embed in a knowledge base into a language model, which is to tell the language model something about entities, so database constants. All right. So here the idea is you're basically going to treat entities the same way the model treats words, tokens. So it's going to have a fixed vocabulary of entities. Each one of these is going to be represented by a vector. Okay. And you can, at any point in the, or at designated points in the transformer, you can do the same kind of prediction over this entity memory that you do at the end of the game, where you predict a word token. You look up something in that memory, retrieve the result, and then fold that into your computation. Okay, so so that's the basic idea, and you also want to give the system an incentive for representing these entities in sort of a consistent, clever way. So one of the incentives is to actually tell it to predict the IDs of entities, so predict which row is mentioned. We have, in addition to language, we also have language with identity, with entity identifiers, which in their training they use Wikipedia hyperlinks. Okay, so in pre-training you'd look like a document like Charles Darwin was a 19th century biologist, blah, 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 and you would have it reconstruct the ID, maybe the Wikipedia, the Wikidata QID for Charles Darwin. And then at the end of the day, you can train it to do other things and they looked at question answering, and they took a natural language question, and the answer was always an entity, so there's just an entity mass that had to be predicted. So this is what they did. This is a bunch of questions from a data set called Trivia QA, where the answers were expressible in this format. So they were entities in the entity memory, which is about 1 million common entities. Not everything, but kind of a lot. And it does pretty well. So this green line is T5. This is a version which has 11 billion parameters. The bluish line is entities as experts, which has a mere 100 million parameters. So 100 million might sound like a big number, but not compared to 11 billion. So it's maybe 1% that size. Okay, it's about 100 times smaller. And this is compared to another large language model, just treating that as a knowledge base. But it does reasonably well compared with even more sophisticated approaches. So the kind of state of the art for these now in NLP is you have some neural process that retrieves a document, or maybe a few dozen documents, or maybe 100 documents, and then you use a neural process an NLP process to read those things and predict answers. So those techniques, and this is from a couple years, a year or so back, so we've got even better results here, but those results actually do perform better than EAE and this pure language model approach. But it's quite impressive how well this works as a language model, which is really what I care about. So now the question is, can I use this extended language model, which knows only really about entities, and extend it so it knows about declaratively stated facts about entities? So this is work that Pat and Hai-Chen did. And this was presented earlier this year at NACL. And the basic idea is kind of similar. So we start out with EAE, which knows about entities. And I add a new memory structure. Okay, so this memory structure is kind of like the structure that's used in MQL. You query it with a concatenation of a relation and a subject entity. And then you use that to look up a value, an object entity. And the way that lookup is done is by basically doing this follow operation. And the subject and the relation are neural variables, and the value can be sort of an aggregation. So this is the basic idea. We're taking this transformer, which now has been augmented with this entity access, and we also augment it with this fact access. And there are a few more details in the paper. But the main thing to notice is the way this fact memory is constructed is that all the entities are basically shared. They're derived. They're the same vectors as in the entity memory. Okay. So these facts are constructed by just taking a representation for a relation, a subject, and an object, and gluing them together. So this is a bunch of numbers. I'm going to kind of try and break this down a little bit. So this is my web questions SP data, which is a little bit easier than Trivia QA. And it's kind of really designed for this task because really you should be able to answer all these questions with the knowledge base. That's the way it was designed. And there are a few different settings here. So this is an old data set. It's based on Freebase. For various reasons, we based our work on the Wikidata knowledge base, not Freebase, which is derived from, but not exactly the same. So sometimes it's better to look at the things which are actually answerable in principle using Wikidata. So that's the right-hand side of this picture. And the other thing is that there was an interesting paper a while back which showed that some things that were considered test questions are actually questions where there's a paraphrase in the training data. Not exactly the same question, but something that's the same up to a few kind of stop words. And some things which look like they're answering these questions pretty well look like they're doing a lot worse when you take away these paraphrase overlaps. So I think the other thing is that this last column where you're looking at no overlap is really the most interesting one. So you can see our model does best, okay? And it's actually doing quite a bit better than these other ones, including EAE and including this very large language model. It does better in the other settings, but I think this is kind of the most important one. It even does better. So this is compared to a model, which again is like 100 times smaller if you consider just the parameters from EAE. Now, the fact memory is basically a whole knowledge base, so that's really big, okay? But it's still not nearly as big as the T5 11 billion model. So we're doing better even than a model which is all non-declarative parameters and 10 times as many of them. And it actually does better than these open book models. If you consider the indexes that are used for this, again, we're much smaller than those models. And we're doing much, much better. And compared to MQL, so that's something that is sort of kind of specifically constrained and defined for these tasks. And again, if you look at the answerable part of the data, then we're doing even better than that. And that's a little surprising because in MQL, we're sort of telling it exactly when and how to access the memory, and in film, we're not, okay? In this fact-injected language model, that's just sort of part of the process of doing the language model. So the other really exciting thing about film is that it is neurosymbolic. So because the entities and relations are represented by continuous vectors, there's a neural element to the representation. But the facts are not neural. They're just constructed by putting together entities the same way you put things together to form a logical term. And you can also add, delete, and modify the fact memory. So very quickly, here are a couple of experiments. So we can take a model. So let's take our last model. We train and fine tune this model. Okay, and what I'm going to do is I'm going to basically try editing things. Okay, so for every test example, I'm going to change the answer to something which is wrong, but it's the same type. Okay, and I'm going to make a corresponding edit to the fact memory. So I'm going to change his birthplace from UK to Germany. All right, and this old one goes away, and now I'm going to ask whether you can get the right answer. Okay, so a symbolic system would certainly get the right answer. Okay. Of course, we don't really know what this fact-injected language model is because it's a language model. It's using all sorts of neural magic to get its answers. And fortunately, if you ask it to answer these things wrongly, it gets the wrong answer. Okay, and if you give it the new memory, it is in fact pretty much indistinguishable from before. Okay, so that seems to work. Another test you can do is you can simulate adding a new fact. Okay, so supposing I didn't know anything about Darwin and I just added a fact about where he was. So that's a little bit hard to do. What we decided to do instead was to basically take the pre-training data, take some test examples, and basically hide everything we know about the test examples. So if the test example is where was Charles Darwin born, then I'd go through and any place where there was a mention in the corpus of Charles Darwin together with the United Kingdom, I would delete that, and every fact in the knowledge base that connected Charles Darwin and the United Kingdom, regardless of the relation, I delete that. So I basically expunge any direct information about the relationship between Charles Darwin, and I retrain the model. So now I've got a model that doesn't know anything about Charles Darwin and many other test cases. And as expected, its performance drops. Okay. So it's still getting some answers right, by the way, which is using this language model magic. So it's, guessing Charles Darwin. It's like, well, UK, maybe, America, maybe Australia. It's just like guessing like an Italian name, maybe. I don't know. We have no idea. It might know that Charles Darwin lived in London and making inference from that. But the key thing is that if you add those relevant facts in without any retraining, it knows how to use it. The performance is again mostly restored. Okay, so this is the bulk of what I wanted to talk to you about. I'm going to mention very briefly a couple of recent projects. So one of them is an extension to the fact-injected language model, which oddly takes us a step away from traditional knowledge representation and back to using text. So we have this symbolic memory, which connects entities and relations. One hard thing is that the relations in the knowledge base are really not the ones people ask about. People ask about, who won the first Nobel Prize, right? And all sorts of things that ontologists might not think to put in a knowledge base. So these aren't great examples because these are knowledge-based relations, but there are lots of relations that people might express in text. So what we can do is we can replace the relation from a fixed vocabulary with some sort of neural representation that's just derived from a single text occurrence. So now each cell corresponds to a particular mention of two entities in text. And the relation is derived from sort of a, a generalized version of that where the entities are hidden. So this is really hard in a number of technical ways. So there are a lot more entity pair mentions in a big corpus than there are knowledge-based triples. And also, the way I've derived this, the relation vector isn't just like sort of a pre-trained vector and all the vector you need is that vector to complete your model. It's derived from this text. That text has its own representation, and you've got a different body of text for every occurrence of an entity pair, right? So naively, all that text would be part of the model, which would be completely impossible. So you have to do a bunch of kind of careful pre-training and partitioning of the learning task. But it works quite well. So here are a couple of cases. So OPQL follow is basically used in an MQL-like model where we kind of know what their templates are and we program them in. OPQL LM is using in a film-like way. And here I'm comparing these numbers a little different because I'm comparing it to other models that use text to answer the question. So there's no knowledge base being used here, it's just using raw text. So this works pretty well. So in the last couple of minutes, I want to talk a little bit more about some other current work, which I'm pretty excited about. And I'll try and make this quick. Entity pairs are designed to get at information that people might ask about that aren't in a knowledge base. But OPQL has a bunch of challenges. So there are too many entity mentioned pairs to store. Way more than the number of documents in a corpus, way more than the number of triples in a knowledge base. On the other hand, that's just looking at pairs, right? A lot of the pairs all by themselves can't answer and model more complex relations that maybe have 3 or 4 arguments. So they're not good for events, okay? And there are a lot of those pairs, just because we have 2 mentions of an entity in a sentence, doesn't mean they're logically, connected in any, or linguistically connected in any interesting way. So how can you find phrases that are connected with a question, okay, and linguistically connected, right? And find these in a way that's sensitive to the sort of questions you're going to be answering. Well, one idea that my group has been exploring recently is by looking at data derived from explainable question answering data sets. So there's a paper recently that came out where somebody was looking at a formalism for explaining a question answering process. So if you have a question like this, okay, we've got a question, we've got some reference to something. So this is an entity reference essentially. And that corresponds to the reference of another entity reference in text. Okay, so these two pink things correspond. Okay, and there's also an answer. Okay, so these are the things that are involved in their explanation. There's a passage, there's question references, and passage references and their answers. So, because this is an explanation of this question, we know that this is that Howl's Moving Castle is an interesting entity, that it's connected to the answer, which is this blue thing. All right, so this is, and we know that something about the relationship. The relationship is described by this question, not by a statement, but it's described the question, who wrote, Howl's Moving Castle? Who wrote this argument? So this is really a lot like a knowledge-based triple, where you've got sort of an abstract version of the question to summarize the relation, okay, the relation, the passage reference, and the answer as subject and object entities. So the question is, can these form the basis of a knowledge representation? And these are quite interestingly different from a knowledge graph. So it doesn't just have binary relationships, because it's often the case you'll have something like, who sang the national anthem at the first game of the 2017 World Series? So these are 2 arguments, and there's a third thing, which is the answer, the singer. Okay, so that's a 3-place argument. These are very common. There's a directionality to the input. Like in Prolog, you sort of have like something you choose as an index. There's sort of a preferred directionality here, which is kind of nice. Everything's from an open vocabulary, so there's no fixed set of things. And some of these are quite interesting. So you have things like, when did the race in Greece take place? So that's the entity, but it's probably not in an existing knowledge base. And of course, it's aligned with the things that are important for text. So I'm going to skip this side point, but this is essentially the current work that's going on in our group. We want to learn models that generate from a corpus of text, so just a corpus of unannotated text, okay, answers to questions, plausible questions, and explanations, where the explanations include these knowledge-based-like collections of phrases. And we can do that because we have existing human-generated explanations for these questions and answers, and we know how to train neural models to extrapolate from those from that human annotated data. So once we've constructed those models, the next thing you do is pre-compute a big database of question, answer, explanation triples. Okay, and this is something that we've also done. So there's a database now of something on the order of 70 to 30 million triples, depending on confidence and so on. So this is a substantial knowledge base that's been produced. The next thing is to learn a model that takes a user question and retrieves semantically similar questions from the database. This is how you can basically do lookup in that knowledge base. So that's kind of the equivalent of the knowledge base retrieval or the follow operation in NQL or MQL. So we've made a lot of progress towards this. And of course, there are other things. This isn't a real knowledge base. You have to be able to recognize when these passages are the same and when relations are the same. And that's a hard problem we haven't started on yet. We, of course, would like to do something that looks more like complex inference. So we'd like to be able to decompose complex questions into simpler questions, or at least have some sort of structured query language over this representation. And that's, again, that's kind of like, that's future work that we haven't really started yet. So this is kind of where we are right now. And just to kind of summarize the questions I've been trying to answer is, first of all, how do we perform reasoning in a neural network? Okay. And the argument that I've been making is that the right way of doing it is a data flow query language that manipulates sets. So these are efficient, they're relatively interpretable, and they seem to be expressive enough for many NLP tasks, even though they can't handle a bunch of interesting things like transitive closure. They seem to be expressive enough for a lot of tasks. The other one is, how do we incorporate reasoning into NLP system? I think the most convenient approach right now is to incorporate them into transformer language models, which are the basis of, as I said, almost all modern work in NLP. And they seem to work for this, right? And these models show a really good performance on question answering, as long as the questions are appropriate, as long as they're covered by the knowledge base. So that's the kind of bottleneck right now, is that these models are good when they're answering expected questions, but the knowledge bases that you're using for are not well aligned with the questions that people ask. So now we can go back and ask this other question of what knowledge do we encode? And that's sort of the current focus of this question explanation database that I'm working on. So that's all I've got. I've got a list of these papers if anyone wants to follow up. I'm sure that's going to be distributed later on. And thank you very much for your attention, and thank all my colleagues for work. Thanks for the organizers for inviting me out here. Or not out here, but I'm going to say out here anyway, because the last ones I've been invited out here were in Ferrara and Rio, and those were fantastic. So again, thanks, and I'll take some questions now if there's time.
Thank you very much for this very informative and, I would say, knowledge-intensive talk. Let's open the floor for questions. Yeah, please just voice the questions as they come up.
Hello. Hi, Paul.
Hi, Nangfazon.
Hello. Yeah, may I have a question?
Yes, go ahead.
Okay. So here you basically vectorize everything symbolic. Queries, facts, predicates. So can we still call it reasoning? Because when you do reasoning, you can never get it wrong. You get a 100% correct. But if you use neural network, you can never get a 100% correct.
Well, I mean, this is sort of like this experiment here, I think. Let's see. This one, okay? So you're right. So the neural network tech, right, which is, let's say this blue was the state of the art at the time, okay? It generalizes pretty well to unseen cases, but it's not faithful to the logical inference, okay? MQL is much more faithful to the logic inference while still having the ability to generalize reasonably well. And, you know, from most of these cases, it's in the 90s. And the reason it's not sort of like, one reason it's not higher in the 90s is because these are a bunch of synthetic queries which include some constructs that are somewhat outside the scope of the MQL representation. So one of the explicit constraints in MQL is that the sets need to be defined over a certain fine-grained type. So you can have, like, you know, a set of computer scientists or a set of cities, but you can't have a set that contains a kangaroo and an ashtray, to use Scott Fallman's example. So if you have sets of things that have nothing in common, but this is a set of synthetic queries where that's possible. And that's one of the cases that are a failure. And it's a failure just because that's sort of something that is not sort of built into the model because it's not important for the tasks I care about. So I think it is possible to have, and if you go to NQL, so NQL, if you ask it to do an entailment query that's sort of in that restricted language, it will give you exactly the right answer, okay? If you ask it to do a hard query, it will give you a set of things where the non-zero support for those answers is exactly the right answer. So you can do these things continuously, right? You can do them with differentiable operations. The question is resolving that tension between generalization and fidelity to like, you know, the intent of an entailment. And I agree that's a complicated problem, but I think there's a lot of progress that's been made on that over the last few years.
Any other question, please?
Yeah, if I can ask a question. So what's your thought on recursive rules, right? This data flow idea of no, just sets queries, and you, as you said, it doesn't work for transitive closure.
Yeah, that's a great question. So I guess there's sort of a couple of I guess there are a couple of answers. My flashback slide from 1993 was looking at pack learnability results, and it's very hard to come up with a recursive version of a subset of Prolog where it is learnable in those settings. Recursion is a very particular kind of like parameter tying, and to some extent, it's intrinsically at odds with doing things in a pure neural setting. So in a pure neural setting, if you just have like a kind of like a neural network without anything wrapper around it, it's a circuit, right? It's doing a fixed number of computations. There's looping in a neural network, but it's all via parameter sharing, and it's looping for a fixed depth. So you can do like depth 5 recursion, right? I mean, so the Tensor Log programs I looked at were written as recursive programs, right? But it was like, you know, some recursion pathfinding on a 10 by 10 grid, right? And you were allowed to recurse 10 times. So it's recursion, but it's all bounded depth recursion. It's not a real recursion. Yeah, that's kind of a tricky point, and I don't really know if there's a resolution to that other than kind of focus on neural things that'll sort of solve the subproblem, and then doing some sort of recursive or, you know, yeah, has some sort of like problem solving thing that calls that as a subroutine, maybe the way Paul described. So that's all possible, but then you end up with these sort of like mismatches between train and test. So in MQL, the only training we did, for instance, was for single steps, and a lot of the testing was on multiple step things. So you can get that sort of compositional generalization, but recursion itself in sort of its full glory, it's sort of out of scope. Good question.
Other questions, please? If not, I have one question related maybe to what logic programmers can do to reduce a little bit this gap between neural and symbolic. Clearly, the cases covered in most of the current research covers data log or grounding involves two propositional or ASP systems. Do you see any value in bringing in the heavyweight logic programming? In particular, unification is a very difficult step in a way, but abstractly speaking, unification is actually something that computes in a lattice of terms, the largest common term that is an instance of the two. So is there any hope for bringing some of the more advanced or more difficult mechanisms that traditional logic programming uses to benefit from some of the more simple mechanisms that are here? Some translations, source-to-source translations, or anything that you think would be a good target for us to work on?
I'm not sure. Am I still sharing the screen?
No, not.
No, I'm sorry, I screwed it up. So it's not important. Just kind of like talk through this. I find that as a scientist, it's extremely important for my students, and incredibly useful for me to understand well the basis of logic, and to understand concepts like unification. And I think those are all based. Those are symbolically idealized versions of things that are people correctly intuited are important operations cognitively. So I don't think those things should be ignored, and I think people that don't know about those are kind of like doing a lot of extra work reinventing things nowadays. And so your example of unification is actually a really interesting case. So unification there's something which kind of surfaces this in these query languages. You've got two sets and you want to intersect them. That corresponds to a unification operation, right? And how do you do that? So in the centroid sketch operation, what you have to do is you have to come up with a common fine-grained type, right? And then you have to sort of like work out sort of the commonalities in the sketch process, okay? So the common fine-grained type is basically a weighted combination of two centroids, okay? And understanding that there is this notion of unification and it's important for reasoning, right, is something that was something that was in my mind when I was designing this query language. Now, what it does is sort of maybe a pale imitation of unification, in that it doesn't let you unify things with complex structures, okay? And I think that's something that sort of does have to be addressed, right? There's a little bit of work if you kind of like scratch your head and look at the knowledge-based completion stuff, where you're sort of trying to leverage relationships and entity similarity. But essentially, if you start looking at even a very simple structure, let's say you've got two entities and that are related by a relation, and those are the output of those relations is the thing that you want to unify. Okay, so how do you do that? So looking at intersections of things that are sort of defined structurally or defined by a bunch of facts. I mean, I think those are like really interesting questions, and some of the work I did in MQL was sort of trying to see whether you could support those things. And I haven't looked at that problem kind of like more specifically. But I think there's a lot of many important analogies that sort of need to be pursued and should be understood. And the things that we can do in sort of a trivial case, like we can intersect two sets, but we can't intersect two structured representations, right? I think many of those things correspond to problems that are being under investigated right now in NLP. So yeah, I think those are like really really great questions, and like sort of looking at this this kind of intersection of these two fields is a very fruitful area. That said, it's kind of hard to get started in neural networks, and it's hard to kind of like stay up to speed just because things are going so fast and there's so much churn, and it's so hard to sort of see what's going on. So yeah, I'm not sure that was a great answer.
Yes, thank you very much. It's as good as it gets in terms of answers, and we'll see what the next few years bring in that field. If we have one more quick questions, we are over time, but it's all very interesting.
Benjamin, raise the hand.
Hi, William. So very interesting talk. I was thinking about this issue of how would you extend this to higher arity facts and also to rules, which are kind of more hypergraphy or more kind of complicated logical knowledge bases to incorporate them here. And I mean, I think your emphasis on arity 2 makes a lot of sense in terms of scalability, training, staying close to what people have already done with neural nets and so on. But one way to try to thread the needle between the two is to work with composite logical expression patterns. And of course, there's a huge space there that one might get into. But if you take human specified knowledge, say logical rules or templates or some of the question pattern, answer pattern, explanation passage pattern stuff as something one could train on to essentially suggest or focus on which particular more, let's call them composite patterns of expressions to focus on, it seems like there would be hope. And I was just kind of wondering, how do you think about how to get beyond the sort of the cliff or whatever of arity 2 kind of stuff?
Yeah, the cliff isn't really arity 2, right? The cliff is sets, right? So if I have a set of database constants, that's relatively easy to represent. So if I ask a question like, I don't know, who are the co-authors of Ben Groshoff, right? That's a set of objects, and we kind of like know how to point to sets of objects, from some, predefined enumerated class. Now, if I ask a question like, tell me like the people that have published papers with Benjamin Groshoff and the year that they published it. So my answer is now a set of pairs. Okay, that's a different problem. So there's going to be uncertainty in that. Okay, so you have a set of your answer is a set of pairs, and there's uncertainty over each of those pairs. Okay, but the problem is what I'm pointing to is itself sort of like a compositional structure. Okay, so I've got to get like Stuart Russell 1996 or whatever, right? And if I don't get those correlations right, I'm not going to have the right answer. So I'm not pointing to things in sort of like a fixed world, okay? So then you get into things which are kind of hard to do in neural networks, right? I'm not even really sure what the kind of mechanisms are, right? In modern deep learning, people just kind of avoid any of this stuff, right? And, there's a little bit of stuff on, kind of tensor-based representations. but that's the problem. So I think the generalization. So I could, let's say, have an arity 3 predicate. So like, if I asked, what was the year that the Beatles released the album Help? Okay, that requires a ternary predicate to answer. Okay, and I don't see a problem with representing that, but every way I can think of to do it that's still based on this kind of set-based language would be, essentially, you're kind of glomming together those arguments and kind of like filtering, things based on that. So it's still sort of a set in and a set out, okay? Or at least it's a set out. So it would be like sort of like, the kind of like way that they look at ternary predicates in Wikidata, where they're sort of like a designated input and output and then a whole bunch of qualifiers, right? So that generalization I can sort of see. I can sort of, I've read, there's beautiful generalizations of this in knowledge-based completion. I don't really know how to generalize these kind of set-based things. And they're so much more efficient than kind of something where you explicitly enumerate all the possible triples, right? I don't, so that's kind of like where I get stuck on it. So I think it's a really hard problem. I'm glad people are working on it. I don't guess that I'm going to come up with an answer to it anytime super soon. Although I think, having like non-binary triples in the knowledge base and being able to use them in the same kind of set-based, set message framework, I think that's probably something we'll be getting to relatively soon. But I think that's just a very shallow kind of way of doing it.
Can I add one more quick question?
Sure.
Yeah, okay. This video is not in my control, but anyway, so you've done just a ton of work, as so many models and languages, just very, very impressive, and at a scale just beyond, infinitely beyond me. Okay, now I can turn on my video. Gosh. Okay, then so what's, I guess the one word is, so what's the role of logic programming? For example, you have Tensor Log, or is it used like does Google use some logic programming, or did you use Python and C++?
Oh, yeah. So I could not get people at Google to use logic programming, right? So Tensor Log, people were like, that's kind of cool, but nobody wanted to use it. NQL, so I mean, this is like completely just between you and me, don't tell my bosses, right? So I've written a lot of papers on this, and there are things at Google where these things work for, right? But this like sort of knowledge level integration of extension to of language models. So it's had an impact, okay? But it hasn't had the impact that I think it ought to have yet, okay? And like, like some people, like this has been like highlighted, at like high levels of the organization, right? It's like, one of the problems with these big language models, they're very powerful, but they're also kind of magic, okay? And there are lots and lots of times where Google wants to give an answer and it wants to not be magic. They want to have it constrained. They want to have it controlled, right? So there are many, many cases where there are like, safety issues and things like that, which are like really important, okay? And I think the problem of kind of generally speaking, how to get neural networks that confidently, that you can be confident will obey constraints or behave in predictable compositional ways. They may not make the neural networks better for the kind of benchmarks, that we're looking at, right? Okay, so it may not actually make it better at question answering than like, the T5 gazillion, 11 gazillion model, right? Okay. But maybe you'll be a little bit more confident that nobody will ask a question, right, and get back some sort of answer which is absolutely horrible, right? That's the danger with these things. It's not that they're, not accurate, right, or that they can never be accurate, right? It's that when you let them generalize, sometimes they'll generalize to things which are, perfectly reasonable behavior on the internet, but not anything that you would want your company or the company you work for to be associated with.
Thank you. Thank you so much.
Well, thank you very much for the presentation and for all the participants. I think this concludes our session today. And if there are any announcements from the organizers, please go ahead. Otherwise, see you tomorrow.
Thank you all again.
See you. Bye. See you tomorrow. Thanks.